I'll give you a brief introduction to the traveling salesman problem, although I'm sure most of you are familiar with it. We'll talk about this Subtour LP and some experimental analysis that's been done with it. And then I'll introduce this outstanding open question that still remains outstanding. We didn't answer it. Instead, we answered a related question that was a conjecture made by Sylvia Boyd and Bob Carr. And then we'll end up the talk with more conjectures and some more experiments. So hopefully a direction forward for trying to resolve this outstanding question. So the traveling salesman problem, it is probably the most famous problem in all of discrete optimization. You're given n cities and you're given the cost of traveling between any pair of cities. And what you'd like to do is find a minimum cost tour that visits all the cities exactly once and goes back to where it started from. Throughout this talk, I'm going to assume that these costs are symmetric, so it doesn't cost any more to go from I to j than from j to I, and that these costs obey something called the triangle inequality. So it doesn't help you, doesn't make any things any shorter to stop at an intermediate city k, one going between I and j. So on the right hand side of my screen here, I have 120 dots that represent cities from a certain country. And you can view the cost of traveling between them as just the Euclidean distance between them. These 120 cities are from what was then West Germany, where it's very easy to pick out the city of Berlin right there. Here's the cost, here's the optimal tour for those 120 cities. So at the time that this was solved to optimality, this was the largest instance of this sort of the traveling salesman problem for which the optimal solution had been provably found. This is an instance due to Martin Groeschel from 1977. Since that time, a number of researchers have worked very hard on coming up with optimal solutions for problems, and there are now much bigger instances of this sort that have been solved to optimality. So David Applegate, I think you're joining in. I saw your face anyway. Here's one of the things that David solved together with Bob Bixby, Lashik Bhattal, and Bill Cook. So now here's 15,000 city instance that was solved to optimality by that team of the now unified Germany. So there's the instance, there's the optimal solution for the instance. And even larger, 25,000 city instance from Sweden, solved by the same team plus one more researcher. There's the instance, there's the optimal tour. There's a researcher in theoretical computer science by the name of Ola Svensson, and he's from Sweden. And he points out that the Swedish population is only 10 million. So these cities are kind of a misnomer. It's sort of the average size would be about 400 people. The way this research got started, take cities from one particular country and think about a tour through them, was started in a very famous paper by Danzig, Fulkerson, and Johnson in 1954, where they were looking at 42 cities from the continental United States. And they were able to solve that instance to optimality. And the method that they use is still the one that gets used today for finding these optimal tours and has been applied broadly to problems in combinatorial optimization ever since. So what I want to do for you now is I want to sort of explain what their methodology was and how it applied to, in particular, to the traveling salesman problem that they tried to solve. So just to simplify our notation somewhat, let's think about having a complete graph. So we have all possible edges of the graph. The cost of an edge is just the cost of traveling between its two endpoints. And what we're going to do is we're going to set up a linear program where we're going to introduce a variable standing for whether or not I use that edge in my tour. Because it's a linear program, I can only indicate that the variable has to be between 0 or 1. But what we'd really like is that it is either 0 or 1, indicating whether the edge is in the tour or not. So the methodology that they use is that they set up a linear program that models the traveling salesman problem. If they happen to get a solution that gives an integer tour, then they can stop and know that they're done and have found actually the optimal solution. Otherwise, they introduce something called a cutting plane. So they introduce a new constraint that's valid for all possible tours, but not valid for the current solution. So it's satisfied by all tours, but not satisfied by the current fractional solution to the linear program. So here's the linear program that they started out with. So the goal is trying to minimize the cost of all the edges that are in the tour, subject to that these variables have to be between 0 and 1, and also subject to the constraint that if you look at any city, and you look at all the LP variables for the edges that are incident on that, that should sum up to 2. And that's because the Tor will have to come into that city and then leave it again. Now, if you go ahead and solve that linear program and get what's called a basic solution or an extreme point solution, you'll get things that look like this. And we'll call them fractional two matchings. So in these fractional two matchings, we're going to have cycles of this where all these LP variables are set to 1, and they are on 3 or more cities. Or they'll look like this, where I have these LP variables in odd length cycles where all the LP variables are half, and then they're joined by paths where all the LP variables are set to 1. If I look at integer solutions of this type, of course, now I only get this type of thing, so cycles on 3 or more cities. Sometimes these things are called subtours, because if you think about it, this is just taking a tour of just those 5 cities and ignoring everything else. So when Danzig, Fulkerson, and Johnson were solving the linear program for the 42-city instance, one of the things that they found is that sometimes they would get these subtours. And so they introduced a cutting plane, an additional constraint that's satisfied by all tours, but not satisfied by those subtours. So they call these loop conditions, but the name that's used now is subtour elimination constraints. So the constraint looks like this. Let's take a set of cities S, like so. These correspond to the vertices that are in the subtour. And we look at all the edges that have exactly one endpoint inside that set and one endpoint outside. We'll call those the edges in the cut for that set of cities. And what we guarantee is that the sum of the LP variables for the edges in the cut has to sum up to be at least 2. And that's exactly because we want it to be the case. We know that any tour is going to have to come into this set of cities, visit some, and then come back out again. Now, the tour could go back and forth across it a couple times, but we know it has to at least come in and go back out again. So that sum has to be at least 2. So here's the linear program that's come to be called the Subtour LP. So the same constraints I showed you before, minimizing the cost of all the edges. Every vertex has degree exactly 2. Across every cut, I have at least 2 edges crossing, and the LP variables are between 0 and 1. For what I talk about later, it's also going to be useful to note that there's an equivalent formulation for this problem, which is rather than having those subtour elimination constraints, I can instead take a set of vertices and just say that I can't have any cycles in that set. Right, so if I take a strict subset of the set of cities and I look at it, it should be a case that the number of edges that both have endpoints inside that set can't be more than the number cardinality of that set minus 1. And that'll guarantee that there aren't any of these subtours in the solution. So an equivalent formulation of the subtour LP is keeping the degree constraints and replacing the subtour elimination constraints by these constraints that said there are no cycles for any given subset of vertices. So how good is this subtour LP bound? Well, experimental work has shown that it's extremely good. So the late David Johnson, who spent a long time at Bell Labs and then at AT&T Labs, did lots of experimental work for the traveling salesman problem. And they report some of the papers that he wrote with McGew and Rothberg, and then later with McGew, show that the subtour LP is in fact very close to the optimal solution. So here's a table from one of those papers. So on the left-hand side here, we have a set of random instances, so points drawn uniformly from the plane and some other types of things. And you'll see that for these instances, the gap between the LP bound and the cost of an optimal tour is more or less than 1% with that exception, where it's 1.01. And then if you look over here, for a set of structured instances that were drawn from what's called the TSP lib, it's a library of standard traveling salesman problem instances, the gap is always under 2%. So experimentally speaking, this bound is very, very close to the cost of an optimal solution. And that makes it extremely useful when it comes time to computing optimal solutions. The gap is very small. And in techniques that get used for solving these things, branch and bound methods and branch and cut methods, having a very strong bound is extremely useful in getting optimal solutions quickly. So that's the practice. What about the theory? How good is this bound theoretically speaking? In the worst case, how bad can it possibly be? And for that, we measure something that we call the integrality gap of the subtour LP, which I'm going to denote by gamma. And what gamma is supposed to be is the ratio of the worst case, possible case between the cost of an optimal solution and the cost of the subtour LP. So given a particular instance where costs are symmetric and obey the triangle inequality, what's the worst case ratio possible between the cost of the optimal tour and the value that the Subtour LP has in that case?
So before
Yes.
following the previous slide practice, don't you need to say something about like how many of these exponential extra constraints you need to handle?
In general, it's just not too bad. I mean, you have to solve a bunch of flow problems repeatedly to actually find that. But in my understanding,
so I presume that's what you meant. So you generate them on the fly. But
you generate them on the fly.
For calling practical, you would need another slide where you say like, on practice we only need to add like I don't know like.
I think in practice is not very much. David Applegate, if you wanted to speak up and tell us how many you need. Although I think actually at some point they stop generating those and start either branching or start looking for other fancier types of violated constraints. So how bad can the integrality gap be? Well, we actually do know that the gap isn't really close to 1, that it's always, in fact, at least 4/3. And here's the instance that shows you that's the case. So it's an instance of a type that's called graph TSP. In graph TSP, I give you an unweighted graph as input, and then I tell you the cost of traveling between a city I and city J is just the number of edges and the shortest path between those two endpoints. So here's the graph. I essentially just have 3 long paths. Let's call the length K. Then the linear programming relaxation looks something like this, where essentially I put weight 1 on all of the paths and then a little bit of weight on the triangles at the end. And so the cost of the LP solution is something like 3K. Whereas if I look at the cost of an optimal tour, at some point I need to introduce 1 long edge that jumps all the way back. And so the cost of an optimal solution is something like 4K. So the integrality gap in this is something like 4K over 3K. I'm hiding a little bit of fudging, but as K goes off to infinity, it becomes something like 4/3. Okay, so the integrality gap is at least 4/3. Now I want to show you an upper bound on the integrality gap. And in order to do that, I have to either introduce or review, depending on what you already know, an algorithm for finding an approximate tour called that's due to Nikos Christophidis. And he showed in polynomial time how to compute a tour that had costs at most 3/2 times the cost of an optimal solution. So what did Christophidis say? He said, first, let's compute the min-cost spanning tree on the set of vertices in my graph. And then let me look at all the vertices that have odd degree in that spanning tree. And let me compute something called a min-cost perfect matching on those odd degree vertices. So I've drawn the matching edges in dashed lines here. What a matching is just a case where I get a single edge that's incident to each one of the odd degree vertices. So I'm matching up those odd degree vertices. Then once I've added those edges to the graph, I have what's called an Eulerian graph. It's connected and all vertices have even degree. So I can do something that's called taking an Eulerian traversal of the edges. I can visit every edge exactly once and come back to where I started. Now what of course we want is something that visits every vertex exactly once and comes back to where we started. So we can use a technique that's called shortcutting. Whenever I come, when following this traversal, whenever I come to a vertex that I've visited before, I'm just going to skip over it and go to the next possible vertex. And because the edge costs obey the triangle inequality, the cost of the resulting tour isn't going to be more than the cost of these edges that were in this Eulerian graph to start with. So here's an example. I'm going to start here. I'm going to skip over this vertex that I visited before. Again, skip over something I visited before. And in the end, I have a tour. And the cost of this tour isn't more than the cost of those edges. Now, to prove that this is at most 3/2 times optimal, the first thing to note is that the cost of the min-cost spanning tree isn't more than the cost of the optimal tour, and this is pretty easy to see. Take a tour, pull out an edge, you have a spanning tree. So the min-cost spanning tree isn't more than that. And then it's not too much harder, actually, to prove that the cost of the matching is at most half the cost of the optimal tour. So those edges together give you something that's no more than 3/2 times the cost of the optimal tour. Okay, so this is Christophidis' algorithm. But what I claimed I was trying to do was trying to give you an upper bound on the cost of this on this integrality gap. So how do we get that? Well, in 1980, Lawrence Woolsey, and then a decade later, David Schmoys and myself, showed that in that proof, you can replace those places where I said within a factor of some factor of the optimal tour within some factor of the Subtour LP. So we can show that the cost of the min-cost spanning tree is at most the cost of the Subtour LP. And the cost of this perfect matching on odd degree vertices is also at most half times the Subtour LP. So the Christofides gives Subtour that's within cost 3/2 of the Subtour LP. So what we end up showing is that Christofides produces Subtour, which was in 3/2 of the cost of the Subtour LP. So certainly the optimal tour is going to be within 3/2 of the Subtour LP. And that proves that the integrality gap is always going to be at most 3/2. So what I want to do now is I want to sort of walk you quickly through this proof. Even though it's an old result, some of the techniques that I'm using in this proof are the same ones I'm going to use later when I talk about some of the newer results. So it's worth seeing. So let's first prove that the cost of a matching on the odd degree vertices is at most half the Subtour LP. And for that, we need to pull out a result from the 60s due to Jack Edmonds that says the minimum cost perfect matching problem can be expressed as a solution to the following linear program. So I introduce a variable ZE for each one of my edges. And now I want it to be the case that if I sum up all the LP variables incident on any given vertex, that sum should be 1, because I want to have one edge incident on that vertex. And also it should be the case that if I look at any odd set of vertices, then I'm going to need to have at least one edge on the inside of that set matched with something on the odd side, outside of that set. And that's just because it's odd, right? I can have a certain, even the number of pairs in here is going to be even. The at least one extra vertex needs to be matched with something outside. So here's an easy way to see that the cost of the min cost perfect matching is at most half the value of the Subtour LP. Just take a solution to the Subtour LP and show that 1/2 of it is going to be feasible for this matching LP. And if I have a feasible solution that has cost that's 1/2 of this, then certainly because I'm minimizing, the optimal solution is going to be at most 1/2. And I claim this is pretty easy to see. The fact that the sum of the LP variables incident on any vertex is going to be equal to 1 follows because it's half of the sum of the LP variables incident on any vertex is going to be equal to 2. And the fact that the sum of the LP variables across any odd cut is greater than or equal to 1 follows from the fact that the sum of the LP variables over here across any cut is greater than or equal to 2. Right, so if I take this solution, take half of it, it's feasible for this, so the cost of the matching here is going to be at most half the value of the Subtour LP. Now I need one more idea, which is just to note that the Subtour LP is non-increasing as I remove vertices from that set. So if I think about the Subtour LP on just the odd degree vertices from the spanning tree, the min cost perfect matching on that is at most cost of the half the cost of the original Subtour. Okay, so this is one ingredient of the proof. We've shown that the cost of matching the odd degree vertices is at most half the Subtour LP. What about the spanning tree part? Well, once again, we pull out of a hat result that's known for a while due to Edmonds that says the min cost spanning tree can be found as a solution to the following LP, where I have a variable again for every edge. I have exactly n-1 edges in my solution, and it should be the case that if I look at any set and I look at all the edges that have both endpoints in that set, I have at most cardinality of that set -1 of them, expressing that there are no cycles in my spanning tree. And that's enough. So once again, we play exactly the same trick, which is to take a solution to the Subtour LP and then show just a minor modification of it is feasible over here. In this case, the minor modification is that we scale down by a factor of n-1 over n. Then it's easy to see that because all of these constraints were met in this alternate expression of the Subtour LP, all of these constraints will be satisfied too. The only trick is just showing that this is satisfied because all of these are satisfied. I'll flash the algebra there. It's not too hard, just a couple of lines, but that's all you need to do. So the costs of because we come up with a feasible solution for the min cost spanning tree problem that's equal to n-1 over n times the Subtour LP solution, the cost of min cost spanning tree is at most that much. And so the cost of the min cost spanning tree is at most the cost of the Subtour LP, and now we're done. I've shown that the Christofides will produce a solution whose cost is at most 3/2 times the value of the Subtour LP. This has been a really, really interesting time to be around for thinking about TSP research, because there's been lots of very interesting progress that's been made on lots of different questions related to the TSP, particularly for these integrality gaps of LPs and for approximation algorithms. So if you think about this case I mentioned earlier of graph TSP, where you get this unweighted graph and costs are just the length of the shortest path, there was a sequence of papers that made progress on this question. So the first real breakthrough was this paper due to Cheyenne, Obice, Garan, Amin Zaveri, and Mohit Singh that showed that they could show the integrality gap was slightly better than 3/2, which was followed up soon thereafter by a paper by Munke and Svensson, which is really beautiful. It's a really nice result. They really bounded things away from 3/2, and then there was a sequence of papers ending so far in 2012, showing that the integrality gap in this case is at most 1.4. Another set of recent progress has been for the asymmetric traveling salesman problem. Now the cost of going from city I to city J is not necessarily equal to the cost of going to J to I. If you think about that case where triangle inequality does hold, and we look at a related linear program, well, it was known for some time that the integrality gap was at no more than a factor of log n. Then 30 years later, so just in the last decade, Subtour et al. Showed that you could do slightly better than that. You could show the gap was at most log n over log n. And that was exciting, mostly because in the previous 30 years, people hadn't done anything other than fidget with a constant somewhere in front of the log. But then more substantial progress was made after that. Cheyenne and his student, Anari, showed existentially that the gap was going to be a polynomial in log n. And then just this past fall, Ulla Svensson, his student, Jacob Tarnowski and Latsi Bey, showed in fact that the gap is a constant. Now the constant is bad, about 5,500, and you can ask how large does n have to be in order for it to be better than that result. But it's progress. Now that we have a constant gap, hopefully we can start driving that constant down. In terms of what we know and as far as lower bounds on the integrality gap, there's this paper by Charkar, Gomez, and Karla that says the gap has to be at least 2. So we don't expect it to be better than 2. If I had to bet, I'd say the gap is 2, but we don't really know. Let's go back to the question we were originally asking, though. What about this case of symmetric TSP where cost obeys the triangle inequality? Well, I claim I tell you that I just told you everything that's known. The gap is at least 4/3. It's at most 3/2, and we don't know anything more than that. Now, there's a long-standing conjecture. It was made explicitly in a paper by Gomez, but it had been floating around for a while, that in fact the gap should be at its lower bound, that the gap should be 4/3. But we don't know how to prove it. Just to convince you how ignorant we are, we didn't, until recently, even know the equivalent worst-case ratio between the cost of a 2 matching, right, these cycles of size at least 3, and the value of the Subtour LP. So Boyd and Carr showed that this gap is no more than 4/3 and at least 10/9, and they conjectured also that this gap should be at its lower bound. Right, a Tor is a kind of 2 matching, but of course there are other types of things that aren't Tors that are 2 matchings. They conjectured that this ratio is 10/9. And the thing that I'm going to sketch in the next 10, 15 minutes is why the Boyd-Carr conjecture is true. So we can prove that in fact that gap has to be at its lower bound. That gap is at worst 10/9. So what I'm going to do is I'm going to show you 2 different things quickly. One is a sort of a combinatorial proof that the gap is at most 4/3 if a certain condition is met. And then how did we end up proving that the gap is at most 10/9? And then we'll get to the section that gives us some more conjectures and some experimental directions to try. So before I get started on showing you the gap is at most 4/3, let me just introduce some terminology. We're going to be playing around with these fractional 2 matchings again. Remember that these are the things where we have these LP variables in odd cycles that have value half joined by these paths where the LP values are 1. So naturally enough, I'm going to call these things path edges, and I'm going to call these dotted lines where the LP value is half. I'll call those cycle edges. And if I have something like this, where removing an edge would break a component into 2, I'll call those cut edges. Okay. So those are my fractional 2 matchings. So here's the strategy of the proof. I'm going to start with an optimal fractional 2 matching. And I claim this gives me a lower bound on the value of the Subtour LP. Remember that we get a fractional 2 matching just by taking out all the Subtour elimination constraints. So if I take out some constraints, the value of the LP solution can only go down. So we'll start with this optimal fractional 2 matching. What I want to do is I want to add a low-cost set of edges to create something I'm going to call a graphical 2 matching. So in a graphical 2 matching, I'll get components that look like this. The size has to be at least 3. Every vertex will have degree either 2 or 4. I'll have 0, 1, or 2 copies of every edge. And why is a graphical 2 matching going to be interesting? Because I can play the same shortcutting trick that I did before to get myself down to a 2 matching. Right? And if I just think about taking a tour on these Eulerian components, and then skipping over vertices that I visited before, I get little subtours on those sets of vertices. So the case that I'm going to consider is when I have a fractional 2 matching where there aren't any cut edges. And what I want to show you is I can add a low-cost set of edges that produce a graphical 2 matching without increasing the cost by more than 4/3. So I'll show you that I can get a graphical 2 matching whose cost is at most 4/3 times a fractional 2 matching. We know that if we shortcut the graphical 2 matching, we get a 2 matching of no greater cost. We know the fractional 2 matching is a lower bound than the Subtour LP. So this will prove that we have the 2 matching is at most 4/3 times Subtour, and that'll prove that this ratio mu is at most 4/3. Okay, so how are we going to prove this? Well, let's start out with some component from the fractional 2 matching. And I said I have these path edges and I have these cycle edges. And what I'm going to do is I'm going to create a new graph from the component where I take every path of these edges and replace it by a single edge that has cost that's equal to the sum of those costs. And I'll take every cycle edge and I'll insert it and it'll have the negation of the cost that it had over here. And I claim that the new graph has got to be cubic, right? Because the vertices that matter are the ones that are on the cycles where they had 2 cycle edges incident and 1 path edge incident. So every vertex is going to have degree exactly 3. It's also going to be 2 edge connected precisely because we didn't have any of these cut edges. So what are we going to do? We'll take this new graph and we're going to compute a min-cost perfect matching on it. So let's draw an orange, say a min-cost perfect matching. And then we're going to use information from those that matching to help us produce a graphical 2 matching from our original fractional 2 matching. So in particular, if I have, let's put the matching down here. If I have a path edge that was in the matching up here, I'm just going to double all the edges that were in that path. Right, so here, this path wasn't in the matching, this path wasn't in the matching, so I don't double those. And for any cycle edge, I'm going to keep it if it wasn't in the matching, and I'm going to remove it if it was in the matching. So these edges were in the matching, so they disappear. These cycle edges aren't in the matching, so we keep them. So I claim that the overall cost here has got to be the cost of all the path edges, plus the cost of all the cycle edges, plus the cost of the edges in the matching, because I precisely doubled all the ones where the path edge was in the matching, and I removed all the ones that I had the negative of the cost whenever the cycle edge was in there. So the first thing I need to convince you of is, in fact, that this gives me a graphical 2 matching. So every node should have degree 2 or 4. And the component size is going to be at least 3 because it was before. So why is that the case? Well, if you just look at a given node on a cycle, right, what could happen in terms of what it gets matched with? Well, it could get matched along its path edge, or it has a matching edge that's one of the cycle edges. If it gets matched along the path edge, I keep both of the cycle edges and I duplicate the path edge and the vertex has degree 4. If it gets matched with for one of the cycle edges, then I remove that cycle edge, keep this one, and keep the path edge, and it has degree 2. And then same thing along the paths, right? If I have a node along a path, if the path edge gets matched, I double all the edges, it has degree 4. If I didn't, it stays having degree 2. So I produce a graphical 2 matching. And let's end up bounding the cost of this solution. So I'm going to let capital P be the total cost of all the path edges, and capital C be the total cost of all the cycle edges. So I claim that the cost of a fractional 2 matching is the cost of the path edges plus half of the cost of the cycle edges, because the LP value was half on all the edges in the cycle. I'm going to claim, and I'll come back and argue later, that there's a perfect matching in that new graph that costs at most 1/3 the cost of all of its edges, So it's going to be most 1/3 times the cost of all the passage and the negation of all the cycle edges. So at most 1/3 P minus C. So let's suppose that that's true. We said the graphical two matching costs the path edges plus the cycle edges plus the cost of the matching. So path plus cycle plus, I said, the matching is at most 1/3 P minus C. And just do the algebra and you get as equal to 4/3 the quantity, the path edges plus half the cycle edges. So we're done. What we've shown is that I produce a graphical two matching that's at most 4/3 the fractional two matching. The two matching is at most the cost of the graphical one, and the fractional two matching is the lower bound of the Subtour LP. So we get this ratio is at most 4/3. Okay. I had this one extra step, which said that the cost of that matching was at most 1/3 times the cost weight of all the edges that were in that graph. And that follows from a little lemma that's due in the F and pulley blank. So they say that any cubic two-edge connected weighted graph has a perfect matching of a cost at most 1/3 the sum of the edge weights. And the proof is really slick, and it just uses this idea that we had before, which is take a look at the LP that expresses the cost of a perfect matching. And what they say is just set all the variables equal to 1/3 for all of the edges. And then they claim, well, that has to be a feasible solution if the graph is cubic and two-edge connected. The fact that the sum of all the LP variables incident on any edge is equal to 1 follows easily, right? If the graph is cubic, it has exactly 3 edges, they all have weight 1/3, so they're going to sum up to 1. The only tricky part is, how do we know that these constraints are satisfied? So let's take a look at some set of odd degree vertices. And let's think about counting all the edges that are incident on each one of these vertices. Right, I have 3 edges incident on all those vertices S. So I have 3 times S. I count every edge that has both endpoints inside the set twice. And I count every edge that has one endpoint inside the set that are in the cut. I count those once. So if the cardinality of this set S is odd, I have something that's odd on this side. This is even. So this has to be odd. The number of edges crossing the cut has to be an odd number. And because the graph is 2 edge connected, I know there can't be just 1 edge across that cut. So if it's odd and it's more than 1, it's got to be 3. Which means that if I'll sum up 3 LP variables that are all set to 1/3, and it'll be something that's greater than or equal to 1. Right? So that's pretty nice. It's a nice little line. Okay, so now I've completed the argument that when there are no cut edges in the fractional two matching, the cost is at most 4/3 times the value of the LP. How do we end up proving this stronger result that the ratio is at most 10/9? What we do in that case is we actually give the LP whose extreme points give us graphical two matchings. So let me sketch a little bit about how we do that. We'll take every vertex in our graph and we're going to make 2 copies of it, I prime and I double prime. We'll say that I prime is required. It's going to have degree 2 in our solution. And I double prime is optional. It may have degree either 2, 0, or 2. So when you think about the combined vertex, it's going to have either degree or 2 or 4, which is exactly what we want. For every edge in the graph, I'm going to create 3 copies of it. One between the 2 required copies of the endpoints and one between the required and the optional, copy of one endpoint and the optional copy of the other one. And I precisely don't put an edge between the 2 optional copies because I want to force every component to have size at least 3. Right, if I'm trying to get a solution where I only have 2 vertices in that one, I can think about joining I prime to J prime. And I've the required copy of I to the optional copy of J. If I do that, then I know that this is supposed to have degree either 0 or 2. If it has 1 edge incident, it'll have to have another. It can't join itself back to the optional copy of I. So it'll connect itself to a required copy of some other vertex. And that'll force the component size to be at least 3. So here's the formulation that we come up with. For every required copy of a vertex, we want the sum of the LP variables incident on it to be exactly 2. For every optional copy of a vertex, we want the sum of the LP variables incident on it to be at most 2. We want the variables between 0 and 1, and then we have this complicated set of constraints that just says across every cut, I want there to be an even number of edges. And you can show that the extreme points of this LP are graphical two matching. So now how do I get from there to proving that the upper bound is 10/9? Well, I play exactly the same trick that we did previously when we were talking about proving Christofides' algorithm. I'm just going to take a solution from the Subtour LP and construct from that a feasible solution here that have cost at most 10/9 of what this solution costs. And we do it in the following way. So suppose I'm given a solution X. Let's take a look at one particular edge ij. I'm going to set the y variable between the two required copies of I and j to be 8/9 times that one, between the optional copy of I and the required copy of j to be 1/9, required copy and optional copy of j to be 1/9. So the sum of this is going to be 10/9 times the sum of that variable. The cost of the solution over here will be 10/9 the solution here. And then you just have to argue that all of these constraints are satisfied. I mean, these constraints is very easy to see, the bounds on the variables. The degree constraints are also easy to see because the sum of the LP variables here incident on any vertex was equal to 2. If you look at the required copies of these edges, it sums up exactly to the edges coming from this LP. So if you look at all the edges incident on the required vertex, that'll sum up to be exactly 2. And on the optional copy, it'll sum up to be something less or equal to 2. All the work is in showing that these constraints are satisfied, given that the Subtour constraints are satisfied. Okay. So that's how we prove that the bound is at most 10/9. Okay, now we get into the conjectural side of things. Conjectures about the TSP go back a ways. So in particular, in one of the papers that Edmonds wrote in the 60s, shortly after he had defined polynomial time, he said that a good algorithm was good if the number of steps could be bounded in some polynomial in the input size. So we call those good algorithms. We call them polynomial time algorithms now. So he made the following conjecture. He said, I conjecture that there is no good algorithm for the traveling salesman problem. Remember, this is before NP completeness or anything, right? I conjecture there is no good algorithm for the traveling salesman problem. My reasons are the same as for any mathematical conjecture. 1, it is a legitimate mathematical possibility, and 2, I do not. So emboldened by Edmonds, we make our own conjecture, which is also a legitimate mathematical possibility, and 2, we have no clue. We conjecture that the worst case for the Subtour LP integrality gap occurs exactly for the solutions to the Subtour LP that are fractional 2 matches. So it's exactly the case where the cut constraints don't really, the Subtour elimination constraints don't really play any role that the worst case is going to have. Now, one of the interesting things about this conjecture is not only do we have no idea whether it's true or not, we don't even know what the consequences are if it's true. Right? If you told me that if somebody comes, an angel visited me and told me your conjecture is true, I still wouldn't know anything more than I did before. Well, I would know something, but I wouldn't know any consequences on the integrality gap from that. I don't know how to come up with a tighter bound on cases in which the solutions are fractional 2 matches than I did previously. One of the threads that came out of some of this recent work on the traveling salesman problem is a conjectured algorithm that might have better performance than Christofides. So it might give us a way to resolve something about this conjecture and come up with a better bound on the integrality gap for the Subtour LP. So here's an algorithm. It's come to be called best of many Christofides. The ideas for it were in this paper by Weiss-Garan et al., and then made really explicit in this paper by An, Kleinberg, and Schmoyes. I'll say more about that in just a second. So what they say is go ahead and solve the Subtour LP and get your solution X. Scale it down by a factor of n-1/n. We said that that's feasible for the min spanning tree LP. In particular, what that means is that it's a, geometrically speaking, it's a point inside the feasible region of what's called the spanning tree polytope. And that means that you can express the point as a convex combination of spanning trees. So here's the idea. If it's a convex combination, that sort of gives you probabilities that it is one of any particular one of a set of spanning trees. So just sample according to that probability. That gives you a spanning tree, run Christofides on that. Rather than computing the min spanning tree, run it on this sampled solution. So they came up with this algorithm for a particular reason that I'll describe in just a second, but we can at least ask the question, experimentally, does this have any hope of being better than Christofides? And this is the question that I worked with the undergrad Kyle Genova to answer. And what we found was the following, is that there is some reason to think that this, empirically speaking anyway, this is better. So over on the left-hand side here, I have a column marked standard, and this is just Christofides' algorithm. Run across a couple of different classes of instances. So these are instances from the traveling salesman problem library. These are VLSI instances, and these are instances of graph TSP. So this is consistent with what the experiments that David Johnson did earlier were finding, that Christofides is something like 9% away from the cost of an optimal tour. For graph TSP, it seems to be at worse. You can be something like 12% away from optimal. We tried a number of different ways of expressing the convex combination of spanning trees and then doing sampling. So if we use max entropy sampling and took the best solution that we found, then what we would get is something that was like between, say, 0.31% of optimal and 5.5% of optimal. Another type of sampling that we did involved something called splitting off. And there we could find that solutions were 0.88% away from optimal up to 6.6% away. So why does this work? I mean, why does best of many Christofides do better than what Christofides is doing? And sort of heuristically speaking, I think the answer is this, which is that this sampled spanning tree that we get ends up having lots and lots and lots of vertices of degree 2, which means that if you look for odd degree vertices, they're kind of few and far between. What this means is that the cost of the matching edges actually are going to be more. Any particular matching edge is going to cost more than it costs over here because the odd degree vertices are far away from each other. But they're going to be a lot fewer of them. And so the cost of the spanning tree, of course, only goes up. This was the min cost spanning tree. But the cost of the matching goes down, and that's enough to offset the increase in the cost of the spanning tree.
David?
Yes, sir.
Kind of a naive question. So is it even possible, or is it even reasonable to think if the whole step of sampling in expressing getting the Subtour LP and expressing in terms of the convex combination, could all of these things be expressible as solving an LP and some careful rounding?
And some careful rounding. Yeah, if you knew which spanning tree to round to, right, I guess you could think about doing that. But I guess you have to be careful about cost too. The other thing that the convex combination, sampling from the convex combination does for you is it lets you say the expected cost is going to be about the cost of the Subtour LP. Right, so you both want certain property. You want to, if you did rounding, you'd have to make sure that your cost didn't go up, and that you were getting whatever properties of the tree that you want.
David?
Yeah.
So in these experiments, when you do best of many, I
Yes.
guess in the splitting off, you can actually take all of them, but in max entropy, does how many matter?
How many samples we draw?
you take?
Yeah, we just fixed the number and did it. So we did something like 1,000 samples and took the best one.
And it's the changing 1,000.
Yeah, I mean,
Didn't
knowing
make
how many we didn't do. I mean, this is where we fell down in our experimental analysis. I think we probably should have varied the amount to see how much better we got with more samples or with fewer. I don't think it was too bad. Just to give you some sense, here's a class of instances. I think these are the VLSI ones, but I'm not 100% sure. If you look at the degrees of the vertices that we got with standard Christofides for computing the min cost spanning tree, only about 60% of them have degree 2, or we have something like 20%, and maybe a bit less than that have degree 1 and 3. But when we do max entropy sampling, now we get something like 90% of the vertices having degree 2, and about 5% of the vertices having degree 1 and 3. So what ends up happening is that the cost of the tree goes up, right? So these are expressed in percentages of the cost of an optimal tour. For standard Christofides, the cost of the tree, the min cost spanning tree is between 80 and 90% of the solution. For best of many, because the value of the Subtour LP is really close to optimal, it's essentially the cost of an optimal tour, that sample. But the cost of the matching really falls down. So here, in standard Christofides, it's between 30 and 40% of the cost of an optimal solution. For these sampled methods, it falls down to be something like between 4 and 13% of the cost of an optimal solution. So this cost goes up, the matching cost goes down, but you win in the trade-off. So how could this result in an analysis that shows something that's better than 3/2? Well, the expected cost of the tree is going to be at most the Subtour LP, again, just by construction. If I sample from the convex combination, it was a feasible solution to the Subtour LP, scaled down by a little bit. The expected cost of the tree is going to be at most that, which is exactly the same thing we had in the analysis of Christofides. What we really have to show is that the expected cost of the matching somehow is bounded away from 1/2 times the value of the Subtour LP. And that's the part we just don't know how to do. It would be nice to figure out how to do it, but I don't know how. There is some hope that this should work, though. And the reason that we should hope that it does work is that it did work. So for another variant of the traveling salesman problem called TSP path, it did work, yes.
Silly question. So,
Yeah.
so in the previous, so that when you showed this best of many works seemed to work better than your cost was for the best solution.
Say it again?
Right? Like your I mean the table was for the least costly solution out
Yes,
of this
yes.
1,000 samples, and now you're claiming something for all of the 1,000 solution, sort of.
This part?
Yeah, I mean like you want
This
to
is,
prove
all,
something
yeah,
about-
this is going to be true just by the way the
no, the second one. So you want to prove something for the expected.
Yeah.
But
Expected would be
I
good
mean,
enough for
in
me.
some sense, you could verify this one as well. Does that hold?
Empirically speaking, yeah, of course it holds.
Because usually the matching is less costly for the best one overall,
Yes.
but like this one also holds empirically that on average
Yes,
it's also.
yes, yeah. So the reason we have some hopes that best of many Christofides might work for regular TSPs, it worked in this special case. So ST-TSP path is this. I give you a fixed start vertex and a fixed end vertex S and T, and then you find the minimum cost Hamiltonian path that visits starts at S, ends at T, visits every other vertex exactly once. So if you do the analog of the Christofides algorithm, it's been known for a while that you get a 5/3 approximation out for the problem. It's also known that if you look at the corresponding linear program, the lower bound on this inequality gap is at least 3/2 by an example similar to the one that I showed you before. So best of many Christofides, I said, showed up in this paper by An, Kleinberg, and Schwois, where they were worried about this problem, and were able to show that you could beat Christofides by using the best of many Christofides, and particularly you could get something that was golden ratio as opposed to 1.666. And since then, there's been a sequence of papers improving on that result. So an improved analysis of this algorithm made this the gap 1.6. And by thinking hard about what properties you want out of a convex combination of trees, people have been able to drive that down to the point where now the inequality gap is known to be 3/2 plus 1/34. So we're really close to that lower bound. Not quite there yet, but really, really close. Okay, I think this brings me to the end of my talk. This is a sign from a radio station outside on JAN MAYEN Island. So JAN MAYEN Island is owned by the Norwegians. It's about, I think it's 400 miles to the northeast of Iceland. So it's in the Arctic Circle and it's cold. I don't speak Norwegian, but I have it on good authority that the translation of the sign is as follows. Theory is when we understand everything but nothing works. Practice is when everything works but we don't understand why. At this station, theory and practice are united so that nothing works and no one understands why. This is sort of the pessimal case about the interaction of theory and practice. I mean, the optimal case is when everything works and we understand why. And the case with the Subtour LP is that it really works, right? And practice is extremely good. And we hope that we can unite theory and practice so that in the end we understand why. So that's the end of my talk, and thank you for your attention. Any questions?
So in
Yeah.
in practice, the branch and bound seems to find is the best.
For finding optimal solutions, yeah, it works really well. I mean, I guess one thing I should have mentioned along the way is that in terms of what you want to run, if you just want a empirically good solution for the tour, is some variation of a heuristic called the Lin-Kernighan heuristic. It's very fast and empirically it's quite well solved.
Instances where that fails,
Where which?
where the branch and bound fails.
Sure, yeah. I mean, branch and bound is, you would imagine that if P is not equal to NP, you should be able to find such instances. And I think there are some instances that are outstanding.
Is there a good random instance, like a random distribution?
I mean, random distributions are easy in the sense that if, say, you draw points uniformly from the unit square, we understand the behavior of the TSP on such instances really, really well. it's known that there's some constant times, the value of the torr is some constant times square root n. So that's not the best set of instances to
Graph
continue.
or high dimensional space.
High dimensional, maybe. I mean, again, that result that I just mentioned for the unit square has some expression in terms of d-dimensional space as well. Other questions? Sorry.
If we show that integrality gap is less than 3/2, does it automatically give an algorithm? Or
Not necessarily. I mean, so I mentioned for asymmetric TSP just a few years ago, there's this result by Anari and Ovais-Garan, and that was not algorithmic. I mean, I tend to think, of course, when I think about such things, I'm thinking in the other direction. I'm thinking about an algorithm that starts with the LP solution, so it's always going to constructively, it'll be constructive. It'll prove the integrality gap by giving an algorithm. But one could imagine a proof that doesn't use an algorithm. Great, thank you. Thank you so much.